So, KSAT. We have two main business areas. One is to be the ground station network for the world's satellites, where we are quite dominant. And we have a separate business area, which is Earth observation. I would say mostly for maritime situational awareness applications. So this means oil spills, as we see to the left, and we do vessel detection, as we see to the right. So SAR data is basically radar data taken up from space, which is very advantageous because it's not sensitive to daylight conditions or clouds, and the coverage is quite formidable, as we see exemplified with the west coast of Norway and having covered a large part of the Norwegian Sea with a single image. So today I want to show you a bit about our results so far, and then what's equally important, at least in my opinion, is the framework and how we approach using machine learning models in production, and finally some research challenges, which are also our motivation for joining the SFI. And Robert, I'm currently not seeing any Teams window, so if there are raised hands for clarification questions, please just yell out. So, SAR image. This is a Sentinel-1 image. The Sentinel constellation is a EU constellation which provides free data, and they can cover as up to 75,000 square kilometers per image. How big is that? Well, if you Google Bjørnøya, that's the small island you see to the bottom left there. So these are around 20,000 times 60,000 pixels, with each pixels being 10 by 10 meters. So this is from a pilot we did. Can neural networks do vessel detections? And we ended up having an error rate, combined errors of both types, below or around 0.5 per image, meaning we do 150,000 square kilometers per error we make. And the cutout both exemplifies how small the vessels are in such a huge image, and also how noise makes the labels uncertain. So we have experts who deliver these services in a manual way, but they are limited by the data they have. And it's of course not possible to have a ground truth, as in being out on the ground and covering anything remotely close to this large of an area. And we also wanted to see how we can do classifying different types of objects. So a nice use case was ice or vessels. This was up around Svalbard for Kystverket last year. Their motivation is to get early notifications of any icebergs due to high risk, especially to the recent surge in cruise traffic in the area. It's an area with relatively few rescue capabilities, and the large cruise ships would be at high risk if icebergs were to come into play. So we took probably the lowest resolution mode possible, which is also because it's one of the free modes from the EU mission, so we are not limited in terms of amount of data. And even when each pixel is 25 by 25 meters wide, we get a very high classification accuracy, well over 90%. These are examples. The color map here is showing only one channel, and it's centered on icebergs and blanked out for land. So as you can see, these are really tiny pieces in the middle, and context matters greatly. But the performance was better than we even expected. So putting the detection and classification together, we can show some examples here. These are, as I said, these are notoriously difficult areas due to ice and actually weather plays into it, even though you can see through the clouds. Storms and wave conditions affect the image, which is the what you see here. This is showing both channels in blue and red and the landmass in green. So in this huge area, we had 3 detections correctly classified, and we had 1 false alarm adjacent to land, which is probably an ambiguity from the radar of sorts, and we had 1 miss, which was I would say it doesn't put the neural network in a bad light. It was a very marginal miss. I think it just fell out of my presentation. Sorry about that. This is in the same area, although land is not included in this image. Again, the neural networks in tandem provide a good situational awareness, missing the vessel as we see here. And keep in mind that we are looking almost at individual pixels here. These are targets a few pixels wide and maybe 10 pixels long in image with 1 billion pixels. The false alarm ice, I think it's a quite clear red target there, and the red channel usually dominates for icebergs, which is probably why the neural network puts this as ice, but maybe it's a case of the ground truth not being unambiguous. And I also included a quite clear, but again, very small vessel, which demonstrates the sort of the threshold that the neural networks operate on. So in terms of these chips, there are thousands and tens of thousands of these chips per image. So you would have to have a very low false alarm rate. We have done some work on oil spills. Again, there are multiple applications. The first one is detection, where what we see on the left, which is the SAR data, is the input, and what you see on the right is the label. But when you have detected oil spills, you can combine the two as input and to a new neural network which seeks to describe the oil spill. So our question going into this was, can we replicate how our experts describe the oil spills to our customers? And in this case, we were on point except for one category. Doing this exercise provided us some very interesting insights, because the neural networks performed quite differently for the different categories. For some it was very accurate, for some it was quite inaccurate. And we took that to mean that some categories were more subjective, than others. That is to say that between the different experts, they might, for instance, some might say that it has variable edges, some may say it has sharp edges. We actually use that when redesigning the categories to make them more precise and more relevant in the next generation. Going on to my favorite part, the framework. In terms of fully automated machine learning neural network approach, this is how you would build a chain to provide a service. So you would detect objects, you would then classify those objects, and you would seek to describe those objects. And then there is a certain point where using other techniques would be better. Currently, for fusing, we have no plans or ambitions to use machine learning directly. And bright spots versus dark areas, that's just to signify vessels and oil spills, respectively. So we are looking at chains of multiple applications, which together can provide value, as we saw with the detection and classification pipeline earlier. So how do we do this? Well, we work systematically at different levels. So we have set up a data warehouse where we combine different generations of the data catalogs or data storages used throughout KSAT's history, and we perform some ETL stuff. It's a bit technical, but the point is that we want to have it all on the same format and very accessible in terms of speed, both to get the data and to see where we have lots of data and where we have little. All of this was very complicated before we started working here, because there was no application for historical data. You delivered a near real-time service and you cataloged your output and you made sure it was preserved for the ages, but not considering how to best expose it and use it later, because we were the first to want to do that. On top of that, we built an API for deep learning tools. The purpose of that one was to take data as input and provide models as output. So when building a machine learning model, we should not have to care too much about what are the different satellite modes and satellite constellations and all of these details. Yes, we can and should configure how we train the model to what fits best for that data, but it's a different thing to have that in a configuration than to have it be a fully manual procedure. With having it in a configuration, it enables us to automate more and more of this process, up to the point where we can now get data and get a model into production with manual effort of less than 1 day. And hosting these models in a production environment, I think anyone who has done on-premise GPU stuff, which I know Robert's group at UIT has done, knows that it's not trivial. It's not without pain, but we are working at it and have got quite a stable solution going. So we can connect it to the other parts of our service, which can be to simulate the drift of icebergs or oil slicks, so we can know where it originated or where it's going, and correlate or fuse with AIS data, etc. The point here being to deliver services to customers. So a small example of a recent improvement we did. Robert challenged me to repeat a demo about this, but my machine luckily crashed this morning, so I was unable to do a live demo just now. But going into this SFI, we identified that we had some utilities, our deep learning API, which was tightly coupled to how we store data and models at KSAT. So this is both bad in terms of collaborating in the SFI, but also in terms of flexibility for ourselves and modern software practices. So what we've done now is that we've made a loose coupling via an interface, and we have enabled the same functionality on local storage as we have with our storage systems. So we can connect to our storage systems, which would give us the full amount of data and ensure that models are integrated into production. Or we can download pieces and set up the same functionality locally to enable collaboration with researchers. And this gives us the benefit that if or when we want to use other external providers for data storage or production environments, we can also combine different steps. That's one of the practical things in a deep learning, machine learning engineers sort of day at work. So I'm not sure if MLOps is known to all listeners. I would think some of you have heard about it. It builds on DevOps, software development practices, which is a way to continuously integrate and deploy code, sort of shortening the cycle compared to having months between releases in previous years. And we are using MLOps, which is to integrate data and models into that loop. So if you think about the previous slides, this shows how we have a system which should also include data and models, and that's what working with neural networks in an industry capacity is all about, really. So I haven't talked too much about the neural networks. That is because we haven't used a lot of time on it. There are now frameworks, software libraries, open source things we can download and get very good performance out of the box. But we do have a special type of data in the SAR data, and we have a few considerations which we really would love to dive deeper into, and the SFI will allow us to do just that. So, for instance, in the top left, we see the SAR data, which is the pink data, and the more purplish with the red and white circles. That's actually the raw neural network segmentation network outputs from the same data. And we have customers which are in particular interested in in accountability of the models we use, and explanations and justification. I think this will align nicely with especially the healthcare part of the SFI. So explainability, and how can we justify or explain the neural network outputs in that sense. And also, even as interesting is to go from the per pixel confidence scores of of a segmentation network output to a per vessel confidence score. So in that image, we see a vessel, we detect it quite clearly, but we only know the confidence the neural networks assigns to each pixel. But the vessel is a more abstract entity, and that's the confidence we're really looking for. To the top right, I've tried to symbolize a data set with augmentations. For SAR data, some of the common augmentations are not valid. You have an azimuth angle, an azimuth axis and a range axis. And in the azimuth axis, flipping is physically valid, but in the range axis, it's not strictly that due to the mapping performed to get it on a sort of on the ground range format. So you have a side-looking radar, and you are looking at angles, and if you flip the image, you sort of break the physics. And the same goes with the side lobes you experience, here exemplified by the strong cross seen at this vessel. This is also a physical phenomena, meaning that rotation is definitely invalid in this data. But we want also to be pragmatic, and we are willing to, or interested in, examining all of these common image augmentation techniques, what's pragmatically valid, what's physically valid, and what's basically useless. Down here to the left, we have the landmass of Svalbard again. Actually, generating this landmass is prohibitively slow with this amount of details, but it's also very crucial to the success of any automated algorithm. So we are interested in the question, can neural networks sort of provide a landmass or enhance a lower quality landmass using the GPUs to perform this much quicker than generating such a detailed landmass using the CPUs and the conventional methods. And down here to the right, I have some of the constellations or satellites we are currently supporting. At least there are a bunch of different imaging satellites meant to signify them. And all of these have their peculiarities with respect to data. And for some of them, we have lots and lots of data. For some of them, we have very little. And we know a lot about model cross-training, pre-training, etc. in the classical or electro-optical domain. We are interested in finding out the heuristics that apply to SAR data, radar data from space. How can we use one of the modes with lots of data to get better performance where we have little data? That's all I had for today. Thank you all for listening, and I hope for some interesting talks now and throughout the SFI.